should be accurate. And in general, people don't show up exactly on time, so we start a few minutes later.
Okay, that's fine.
Do it from the center, so that you can hear it.
Oh, okay, because I don't have a mic.
Correct.
Oh, I see, okay.
They will turn on an exterior one to pick you up.
I see.
And thank you.
No, because it hasn't come yet. But I will check the stuff that's in.
Oh, you haven't checked yet?
Yeah. Because there's a whole bunch of stuff there. I think that might be. Yeah.
Okay.
Because I got like. Yeah. Bobby has some stupid. I have a really old one. Yeah. Well, I'll tell you when it is.
Sure. It's going to take you time to transfer that choice. Thank you.
So on the local block, it says...
Hello.
Do you know where these offices, Bobby?
Oh, yes, it's the
It's
second
right
floor.
across, yeah, it's right across from that. So it's the second floor into the back.
Oh, that sounds good.
Do you know where that seating area is by where National Mars?
Yes, like the
Right next
ITC
to it.
lounge.
Yes.
Amazing.
They all have their name on the system. That's not mine.
Oh. It's the only time you're playing.
Don't play too much or we'll take it away from you. I think let's go.
Oh, okay.
Thank you.
So, hi everyone. I'm very pleased to introduce this week's ITC Colloquium speaker. It's Ressler. He obtained his bachelor's degree in physics and applied math in North Carolina State University in 2013 and finished his PhD in physics at UC Berkeley in 2019 on predicted models of Galactic Center accretion. After his first postdoctoral position at UC Santa Barbara, he has moved to his current institution, CITA, I think, for his second postdoctoral position. He is an expert on both semi-analytical and numerical works on accretion disk around black holes, plasma physics, and fluid dynamics. And he has used a novel technique that enables simulations to cover a wide range of dynamical scales, and I believe he'll talk about this today. So please take it away.
Thank you. Yes, thanks to the organizers for having me. It's a pleasure to be visiting Cambridge and have the weather actually be better than where I left. For 9 years I was in California, I could never say that. And now I have the misfortune of living in Toronto. But today, yes, I will be talking about multi-scale simulations of accretion in the Galactic Center onto the supermassive black hole Sagittarius A star. And I call it a smorgasbord of results because I'm going to not go into great detail into any particular result, but show a wide variety. And actually, I have much more prepared than I need. So at whatever point I need to, I can just stop and go to the conclusions. So I won't go into any great detail, but if you want to have more detail, please just talk to me or email me or see the paper, which is not published yet or even submitted yet. But eventually it will be, and then you can see the paper. So stay tuned for that. So a lot of this is unpublished. So all of you, I assume in this room, are very familiar with this. Some of you are intimately familiar with this image, but it just gives us a nice starting place and background for the work. Of course, this is Sagittarius A star at 230 gigahertz, resolved by the Event Horizon Telescope earlier this year. At least that's when the data was released. Of course, the data was taken several years ago. But this comes at an exciting time when also, in 2018, the interferometer gravity in the near infrared detected flaring motion that orbited around the black hole on about the scale of 10 gravitational radii in a clockwise motion. All that to say that this is a very exciting time to be studying horizon scale accretion flow, and I'm fortunate to have come into the field at a very exciting time. Now, to model the horizon scale accretion flow, for simulation purposes, you have the basic equations of fluid dynamics, conservation of mass, conservation of energy, momentum, and then the Maxwell's equations for the electromagnetic field. And of course, this is all in strong gravity, so all these equations are much more complicated than they look. Einstein notation looks very elegant on the surface, and then you dive deep into it, and it's a nightmare. But of course, you just put those equations in the computer, and they can solve them.
What about J mu on the right side of Maxwell? There is a current usually. You don't have that?
No, isn't that included in the F?
Oh, you can, if you put
Yes.
the star to include the J, I guess. It's not the electromagnetic.
Yes, I may have made a typo there.
Okay.
Um,
But it's not in vacuum, right, the Maxwell's equations? You're not doing it in vacuum. I mean, there is a plasma.
yes,
Right.
yeah, right. And then you can you put some initial conditions. So for example, a torus around the black hole in hydrodynamic equilibrium seated by a weak magnetic field, which is then unstable to the magnetorotational instability and accretes inwards. This is just a very low resolution simulation from Chris White. And you see, just to give you an idea of what happens, of course, I'm assuming many of you have seen simulations like this before. So yeah, very low resolution, why it's so diffuse and smooth. But it was just for illustration purposes, so don't blame Chris White for running such a low resolution simulation. And of course, by now, over the past 10 years, many people have been running these simulations with a variety of codes and getting to very high resolution, studying all kinds of cool things like tilts and breaking of disks, and then even plasma instabilities at super high resolution. And the Event Horizon Telescope itself has made a wide library of these kinds of simulations in order to constrain properties of the accretion flow. And from that, we have a series of things that we know, some that we're not sure about, and some that we don't know. So what we know for absolute, well, not absolute certainty, but pretty certain that the black hole has a mass of 4 million, so roughly 4 million solar masses based on stellar dynamics. We've known that for a very long time. What we're pretty sure about now is that the accretion flow is roughly face-on near the horizon. We know that both from those gravity flaring results, the way it orbits, and then, of course, the 230 gigahertz image, the way that there's multiple hot spots at various angles, so it's more or less pointing face-on, and this is consistent with the EHT analysis. Then relatively strong magnetic fields near the horizon. We know that from the gravity results as well and other polarization studies.
What do you mean by strong?
Beta of a few.
How many kilograms?
How many kilogram? What?
Kilogauss.
Kilo what?
Gauss?
Oh,
Gauss
Gauss.
is
Gauss.
units of magnetic
Yes. Gauss, 100 Gauss.
Oh,
-ish.
100 Gauss.
Yeah.
Okay.
The models tend to favor, so something we're not sure about, but this is what the model suggests, that there's a higher black hole spin and that the flow is magnetically arrested, which I will discuss in the next slide what that means. What we're not so sure about is the time variability. None of the models seem to do a great job at modeling the time variability of the emission, and then whether and where and how much there are non-thermal particles that get accelerated to high energies, and how these relate to infrared and X-ray flares. And then also, we don't know whether or not there is a jet in this system. There's no obvious signature of the jet. There's some not so obvious signatures that some have suggested is a signature of the jet. But if it is strongly magnetized and highly spinning, then you would expect there to be some kind of electromagnetically powered jet, but we don't see obvious signature of this, so where is it and why don't we see it?
About the things that we might know, why is the accretion flow sort of perpendicular to the plane of the galaxy?
You mean like just why did it happen to be that way?
Yeah.
I have no idea.
Isn't it a small probability also because the vector
Yeah.
pointing at us?
Yeah,
is
I mean,
small? It's unusual.
yes.
But also if there is a jet,
And also M87 is sort of pointing at us too, so it's a bit odd.
but the jet will point at us if it
Yes,
exists.
yeah, so that could be one of the solutions to the jet
Ah.
problem. Yeah. So this will be important later, and also just to describe the magnetically arrested disk that I described before. So of course, in 2003 and slightly before this, Ramesh proposed this idea where if you get a lot of magnetic field accumulating near the horizon, it can become so strong that it interferes with the inflowing accretion, which will then ultimately lead to these eruptions of flux where the magnetic field escapes in these buoyant bubbles and even pushes back against the accretion flow, as you see in these simulations. This accumulation tends to bring it to this value of the magnetic dimensional measure of the magnetic flux, which is the absolute value divided by this thing proportional to the square root of the accretion rate. It tends to saturate around 50 to 70. That is with some factor of 4 pi that some people include and some people don't. So it could be 15 or 50, but for the units I'm using, it's around 50 to 70. And then what you see is like limit cycles of flux rising, then slowly dropping, which is at a point of flux eruption, and then it relatively slowly increases again, then drops again, and so on and so forth, and it keeps going. So that's the basic idea behind the magnetically arrested state. Now I just...
For the sun, the magnetosphere, is the beta in this, like corona? What's the value of this?
In the sun, I think it's... I'm no expert, but I think it's somewhere... It's above 10, I believe.
Okay, so it's not
relatively high beta.
Yeah, so it's not very far from what you are dealing with.
Yeah.
The corona.
Yeah, so some of the results in the solar wind have been used for these accretion flows. So it does help to have that information. So for these simulations, you tend to start with initial conditions that I described. So in general, not in general, but the majority of the case, these initial conditions are some kind of equilibrium torus with weak magnetic field lines. And I break down the features of these initial conditions as things that are chosen, fit, and ignored. So what is chosen is the field geometry. You can choose anything you like. It's generally so it's weak enough that the initial geometry doesn't really matter that much in terms of affecting the equilibrium, but it does matter in terms of the resulting state that you get. And then you can also choose how bound the torus is, which is how thick and or the temperature. Really, it's the entropy is the variable that we tend to work on. Then what you can fit is the mass of the torus, because these simulations without radiation are completely scale-free, so you can just scale up up and down the mass until you get approximately the right emission at a certain frequency. It tends to be 230 gigahertz for obvious reasons. And what is ignored is anything outside of this, if there's any other source of accretion or anything that would not fall into this paradigm. And how you use these simulations to constrain parameters, you tend to think of some kind of torus that you want to run, and then you run it, see what happens. You make some predictive spectra, so this is just the spectra as a function of frequency at very low resolution for some reason. I apologize for that. And then you make a predictive image, and you compare it to the actual data, and then you go back to the original initial conditions and just run a suite of simulations and keep comparing, and then you can start constraining observations. And this is a great way to do it. You can learn a lot about the accretion flow. You can run a whole bunch of models all at once and learn a whole bunch. But there's another way to do it, and I took inspiration from a quote I found on the internet by Reggie Watts, who I actually have no idea who this is. But when in doubt, zoom out. And so what do I mean by that? So for Sagittarius A star, we have the convenience of being able to roughly resolve the Bondi radius, so where the source of accretion. And what we know about the system is, so Sagittarius A star right there. There's also all these other point sources. This happens to be a pulsar wind nebula. Ignore that for now, or ignore that for the whole talk. And there's also other point sources, some of which are Wolf-Rayet stars, which are stars with very strong stellar winds, high mass loss rates, relatively high wind speeds, and there's 31 of them known, which is a relatively large amount just outside the Bondi radius. We believe these are the primary source of accretion, because even a fraction of one of those winds can source the entire accretion flow. So there's a whole bunch of mass sitting there, or being provided by those stars. And then just from fitting the spectra, that we have the temperature at this Bondi radius is roughly 1.3 keV, number density 26 per centimeter cubed, and the Bondi accretion rate is 10 to the minus 6 solar masses per year. That's the Bondi accretion rate. The actual accretion rate is much smaller than this. I think that might be actually a little low. I think it's actually higher than that. I might have made a mistake in that.
What's the Birra temperature at this Bondi radius?
I think it's something around.
Around this.
Yes.
So this is just the temperature above which things will flow out.
Yeah. Yeah.
And so you need to make sure that it's not outflow. It's
Oh yeah, no, yeah. This is just the estimate of the Bondi. It's just
Right.
like I don't use this for anything other than comparing it to the Bondi accretion rate. And actually, in fact, I will show in a second that a lot of that is outflow. And so you could study this scale using simulations as well. Of course, you don't need general relativistic simulations this far away from the black hole, but you can put these stellar winds into sources in your simulation. So these are all the Wolf-Rayet stars. This is work done by Jorge Quadra and collaborators over many years. Very nice work where they put these stars into a simulation, let them orbit, and compared to, for instance, the X-ray emission, and showed that it can produce pretty well the overall integrated X-ray luminosity. And so what I want to do is connect those two scales. So we have the Bondi-scale simulations and the horizon-scale simulations. How do we connect them? You would like to have a simulation that span the entire dynamical range, but of course that's like 6 to 7 orders of magnitude, and that is impossible by anybody's computational standards at this point. But what we tried to do, or what we did, is you take this large-scale wind simulation, you take some of the data from the simulation, you put it into a smaller simulation as initial conditions, run that for a while, take that simulation, make that initial conditions for a GRMHD simulation, run that for a while, and then you have effectively a GRMHD simulation that is sourced by winds. And I particularly use a Cartesian box with a whole bunch of mesh refinement to do this, because there's a priori there's no obvious special direction for the rotational axis. So to show you what this looks like, this is just a simulation of the winds on the large scale. I think this scale is about half a parsec in halfway, so the whole thing is like about a parsec, which is maybe 10 times the Bondi radius. And then so you see a lot of this stuff provided by the winds goes to outflow, and just it all eventually becomes a almost spherical Parker wind. But some of it does accrete. You can see some of this stuff. There's little clumps that form and other things going inwards. And that small fraction then ends up as initial conditions for the smaller scale simulations. One thing I will mention briefly is what I also include is electron thermodynamics. What do I mean by that? So unfortunately, Sagittarius A star on Bondi scales the fluid is collisional-ish. So collisions are relatively important. So they're on dynamical timescales, you expect to have many collisions. But then when you go down to the horizon scale, the flow is very collisionless. So you wouldn't expect it to obey the normal laws of equilibrium thermodynamics. So instead, you have to have some prescription for the electron temperature. What we do is we take the equations that we have, and this implies some kind of some dissipative heat, non-adiabatic heat, and you take that and you apply it to the electrons based on you give some fraction of this to the electrons based on what we know from particle simulations. This is a particle and cell simulation. And you give some fraction of that to the electrons and some fraction to the protons or ions. And so the prescriptions we use, there are two different types. There's turbulent heat, quote-unquote turbulent heating. So heating that would be just pure MHD turbulence, where electrons get most of the heat when the magnetic field is relatively high, and ions get most of the heat when the magnetic field is relatively low. On the other hand, there's reconnection heating, where they both get about an equal amount of heat. So we include both of these. I won't go into great detail in the results for this, because I think it's perhaps the least interesting of the results. But this informs all the results. So when I'm calculating emission, I'm using these various heating functions. So just to be.
Do you have a power law component or not?
No.
Okay, because some people claim.
Yes.
Yeah.
Yeah, it's very likely that they are there, but it's hard to know what to put in. There's the parameter space is so wide. And also that at 230 gigahertz, that's likely not important. Okay, so just to outline the main parameters of the model, we have the magnetization of the winds. So I should have mentioned this, but the winds in the simulation are magnetized. They have some magnetic field in the winds. And so we parameterize the magnetic field as ram pressure of the wind divided by the magnetic pressure. And then we have the time at which I restart the original large-scale simulation to feed into the smaller scale simulation, then the electron heating fraction. But really the most important parameter of all, it turns out, is randomness. As the wisest man who ever lived once said, time and chance rule them all. And that tends to be the case with these simulations. What do I mean by this? So take a look at these two simulations. They look very, very similar at this scale. This is half a parsec scale. The magnetic field lines are plotted in yellow with arrows, and then the density is in high is white, low is green. Looked very similar. But then if you just go to 10 times smaller scale, they look completely different. So these very small differences in these two images lead to very large differences at small scale. And when you're going from 5 to 6 orders of magnitude down in scale, very small differences at large scale can lead to very large differences at small scale. And so what ends up happening is that even if you change things in the original simulation that should not matter, like numerical parameters, like the reconstruction method, which is, not to go into detail, but how you interpolate to cell faces from cell centers will change results in the smaller scale simulation. And that is very discouraging if you're looking for a single model that is the definitive simulation for Sagittarius A star. I believe that these simulations cannot produce that because of this issue. On the other hand, you can just run a suite of simulations and sort of get general principles from the simulations and also see what is robust and what is not robust. So that's what we did, and that's why I call this a smorgasbord of models, because I just ran a whole bunch of different types of models. So different magnetization of the winds, different spins of the black hole, and then different realizations, so changing various little parameters in the simulations. And the nice thing about a smorgasbord is you can take what you want and leave what you don't want, and there's no particular order in which you're supposed to eat it, or you're not obligated to eat all of it either. And I should mention that for the spin of the black hole, I put that into the plane that points directly away from the Earth. So it's spinning, like if you're looking in the plane of the sky, it spins clockwise. And this is based on the gravity and EHT results. So I had to choose a direction for the spin, and I figured that was the easiest way to just fix the spin in that direction and see what happens. So what are the robust features of the simulation? So one thing that is relatively robust, or that is robust in all these simulations, is that strongly magnetized flows seem inevitable. And by strongly magnetized, I mean beta of a few, so 2 to 3. And these are two different simulations, one with beta wind of 10 to the 6, and one with 10 to the 2, so a wide range of initial magnetic fields. But as you fall inwards towards the black hole, you eventually saturate at the same beta value. So it would require an exceptionally small magnetic field in the winds to not end up saturating at beta of a few. So that seems to be relatively safe to conclude that it's fairly highly magnetized. Another thing that seems to be relatively robust is that the density profile / accretion rate, which are essentially the same thing, are consistent with observations. So the observations, this is a combination of various observations just put into like a few power laws for convenience, is the white dashed line or dotted line. And these are a couple of the simulations, and they're relatively consistent with this r to the -1 scaling and even in magnitude. So that is, at least we're getting something reasonable. And we can, it's reasonable to analyze the simulations further if they're agreeing with them. And
Where does that r to the -1 slope come from exactly?
in terms of the physics, we don't actually know. So this is something that's been puzzling us for a while. There's an argument for why you might get r to the -3/2 and r to the -1/2.
That's
so,
m dot equal constant.
Yes. So r to the -3/2 is just Bondi accretion.
Right.
M dot is constant. R to the -1/2 is if you have convective dominated flow, where everything is just, you basically have m dot is 0, and so everything circulates. So r to the -1 would happen if you have p dot is constant, which is the momentum is constant. So you could argue that that would be this type of flow, but if you actually look at p dot in the simulation, it is not constant. So that rules out that explanation. It's a very nice explanation, but it doesn't fit.
But it means there is some outflow also, because
Yes, there's definitely outflow.
So maybe it's a three-dimensional thing, because
Yes.
you have outflows along
Yes.
the poles and then
Yeah.
accretion along the
Yeah,
quaternion.
and it might just be, well, it's somewhere in between. The -1/2 is the extreme, -3/2 is the extreme, so that's
How
gives
does
us
it
-1.
relate to the gas equation of state in that sense? Like,
What
You
is
mean
the
in term-
temperature?
yeah, like if how the pressure builds up with compression kind of relates to how much inflow versus
Yeah.
So
outflow
he's
you
asking about
have.
the temperature profile. What
Yeah.
is it?
It just follows the virial scaling. So
Interesting.
Yeah.
Yeah. So then it's kind of like you have per like decade. Do you have like the same amount of outflow and inflow like
Yes.
fractionally?
Yeah.
Yeah.
yeah,
Because it's like you're always virialized at every
Yes.
radius.
yeah. So
Very
there was an
interesting.
argument we had which we thought was really nice and thought worked, which was that if you have a particular distribution of angular momentum with accretion, like with wind, not accretion rate, but wind mass loss rate. If there's a particular distribution, which we would actually expect in a single wind, then you get this distribution of, you get this particular scaling for the density. But then somebody else ran simulations that have nothing to do with winds at all on this large scale and also got R to the -1. So we're trying to figure out why this seems to be so general. And I think Ramesh and Kaushik just recently had some simulations that they ran for a long period of time, mad and saying that both scaled as R to the -1 as well.
Yeah, so I was going to ask, what's responsible for keeping it virialized, the field, or is it the fact that you're injecting it with the orbital velocity of those?
Yeah, I think it's the heating.
The heating.
Yeah.
But what is the radial velocity versus radius?
It depends on whether you average it or you take the average of the actual radial velocity or radial velocity squared. So if you just take the average of the radial velocity, it's much lower, and it doesn't have a nice scaling. But the square root, the RMS, also scales virial RMS velocity.
Okay.
Thanks.
So electron temperatures, if anybody's interested, I'll go back to that. I think there's more interesting stuff coming. So now I'll move on to things that I would say are general principles that you can derive from the simulations. So you can't necessarily say that this will always be the case, that one particular run will be the definitive solution, but you can say if this happens, then this happens, that kind of thing. So one thing that tends to happen is that the accretion flow often comes in tilted. So this is on 2000 gravitational radii scale. If this is looking into the plane of the sky on the left, the top is looking in the plane of the sky, the bottom is looking perpendicular to the plane of sky, so rotated. So if you're looking, so this one would be roughly face on for us. This one is roughly edge on, and these are. So you can get both of these situations. And so since the black hole spin is into the plane of the page, this would be completely aligned. This would be completely perpendicular. And so 5 of the 8 simulations that I have are significantly tilted. That's just for a representative number. Then it's magnetically arrested sometimes, but not always. So it's not important what exactly these individual lines are. So 2 of these are just for comparison. So these 2 are these 2. Those are the same. But so some of them become magnetically arrested. In fact, quite high value of this phi BH, which is even above 60, so it's roughly 70. The typical value is like 50 to 60, so it's a bit high. So there's slightly more magnetic flux there than a typical torus simulation. These other 2 also become mad, but then 2 don't, and they seem to be happy not going mad for a while, though they do reach, some of them reach the mad state or not the mad state, but they reach the mad level of flux at certain times. And so 6 out of 8 of these become magnetically arrested. It seems like magnetically arrested is more common than not, but it's not definitively, it's definitely going to be mad from just these simulations. So now I think this is perhaps the most interesting thing is the tilts. So this is the case where you have the initial tilt is completely, this is 90 degrees, so it's completely perpendicular to the black hole spin. Black hole spin in both of these movies will have black hole spin pointing up. And so in this case, the accretion flow started, I think it's, no, so yeah, going around something like this. And then this one, it's roughly 45-degree tilted. This one happens to be sane. This one happens to be mad. And if you look at the sane case, you can see it starts off, oh, sorry, it's rotating counterclockwise. It's sort of fighting against the accretion flow, and the jet are fighting against each other. Eventually, it does seem like the black hole wins in terms of aligning the accretion flow, eventually. But then takes a while. So it sort of starts to win at this point. And now the accretion flow is completely aligned, at least on this scale. But then as time keeps going, it sort of dies off, and the accretion flow starts winning again. Yeah, around here. So what happens is that when the jet was very powerful and the accretion flow was aligned, that was when the magnetic flux was almost to the mad level. That was a peak in magnetic flux. But then if you remember the curve afterwards, after that the flux sort of leveled off and sort of stayed around a modest value. And this is now the modest value state where it's continually fighting, but nothing, the accretion flow is more or less winning over the black hole spin. Yes?
If you explicitly measure the jet power, wouldn't it be that the jet is just pointing away from the emission plane?
Yeah, the jet power goes down as well.
Okay.
Yeah, so it's not just pointing away. And then for the mad case, you have so initially the jet is, so it's not quite a fair comparison because this was only tilted by 45 degrees, but that's not really something, I can't control the tilt. It's just a function of whatever happened at large radii. So this one is mad and tilted by 45 degrees. So as soon as it goes mad, it's not mad initially, but as soon as it goes mad, the jet and the accretion flow almost completely align, and they stay that way for the rest of the simulation. And in fact, the amount that the accretion flow aligns and the jet aligns becomes, in terms of radius, as time goes on, the radius goes outwards that it aligns. So it just keeps aligning at larger radii. So, and if you can look at this, so this is a very long movie. I need to hurry these things up. But yeah, it just keeps going, moves around, it's chaotic, you know. There you see the mad outbursts. Just to look at the actual angles, so it's a lot more, it's even more striking if you look at the angles. So these are, so just look at the solid lines. The solid line, the white is spin 0, so tilt in this case is just angle from the spin axis, or what the spin axis would be, so the z direction for a equals 0, because obviously there's no actual tilt when a equals 0. But when you turn on the black hole, that's the purple. So there's definitely, so this is at 3 different radii, 5, 20, 50. 50, it gets aligned, so the peak, this is peak value of flux is this spot right here, about 30,000. And that is when you see the most alignment. But then at other times, it's sort of in between. At large radii, it's more or less the same as it was when a equals 0. Small radii, you have a bit more alignment, but still not as extreme as the case when you have the magnetically arrested, where it just plummets to 0 for small radii. For large radii, it just slowly goes to 0, as I mentioned. And this dotted line is when it becomes mad. So right when it comes mad, so I found that interesting. And a similar thing happens with the jet. The conclusion is basically the same, so I won't dwell on this for a long time. I just think this is a cool movie. So the black hole spin is up in this direction, and this is on a few hundred gravitational radii scale. So the jet is actually going perpendicular to the direction of the black hole spin for a while. And then it does the same thing. It starts to align, and then it goes back to being more or less perpendicular. This is a 3D rendering. It's not the greatest 3D rendering in the world, I'm sorry. But every time I try to, I get very frustrated making these 3D renderings. And so as soon as I get something that looks reasonable, I kind of stop. But yeah, so it starts aligning, and then you get this very odd happening in a second where it kind of like curves over itself and then disappears. So what I believe happened there is that the jet ended up was then pushing directly against the inflowing accretion. So it was actually pushing against the supply of magnetic flux. So it started killing off its own supply. Never mess with your own supply, that's what they say. But that's what happened, and then that's what I think happened. And then it has to slowly build up flux again, and then you get more jet. And then in the MAD case, you'll see that it aligns more or less eventually in a very long movie. Oops. Dang it. Yes, a question?
Yeah, so the only parameter that determines, or not really a parameter, so whether it's matter saying and the initial tilt is just set by large scale fluctuations? And you
Yes.
just pick these?
Yeah, it's set by a combination of the, so it is set by, in some ways, by the parameters like the magnetization in the winds,
Sure.
but in a very not obvious way. Like, for instance, the difference between the one that was aligned and completely perpendicular in the initial, in the accretion flow, like coming in, was one was highly magnetized, one was not so magnetized in the larger scale. But then at other times, that is not the case.
But does that let you tune MAD versus same?
Not really, no.
Huh.
Yeah, unfortunately. I mean, sort of, unfortunately, because I guess that's what I was going for. I didn't want to be able to tune it.
Sure.
But are you assuming a vertical magnetic field in the initial conditions?
No.
And then- no.
No, so what I assume is that every wind has a poloidal magnetic field in the frame of the wind. So it wraps around the wind. But what ends up happening is that since only a fraction of the wind will accrete, that whatever magnetic field you have in that little tiny fraction of the wind kind of looks vertical on small scales.
Okay.
So I think that's what happens.
Did you consider looking at a toroidal field geometry?
In terms of, well, it is kind of toroidal in the frame of the star. It's not obvious how to get a toroidal field like from, like just putting how you would put it into the wind to then ultimately get a toroidal field. Because there's like toroidal in the frame of the star and toroidal in the black hole frame. So in the black hole frame, I mean, we kind of have situations where there's not as much vertical flux, which I'll talk about in a second. But I think physically, we're pretty solid that the field in the wind should wrap around, just because the way the flux freezing happens, you're so far away from the surface of the star that the only component that will survive is the phi component, because the radial component scales as 1 over r squared, and the phi component scales as 1 over r. So what we don't know is the direction of the phi, like what is the phi direction. But so we do that random for every star.
Since this is so chaotic and dynamic, if EHT is right and gravity is right, and we happen to be looking at Sagittarius colon, do you think that's basically just random and meaningless?
I think it could very likely be that the black hole spin is what causes that. But then that could be, I don't know what causes that. So I don't know if that's random and meaningless. I don't know if that's like a philosophy of life. But yeah, it depends on whether it's spinning or not. There is one direction that rises above the randomness. That is the stellar disk, the clockwise stellar disk, in which about half of the Wolf-Rayet stars find themselves. So if I had to bet on a single incoming angular momentum direction, it would be that one, which is aligned with the disk. So that would be the case of, I believe that is the almost face-on case.
What fraction of the time is the small scale flow that you remap? Like, what fraction of its angular momentum vectors are relative to that? That wasn't a complete sentence, but I
Yes.
think you know what I mean.
Yes. I would say, So it's complicated, because the more magnetized the winds are, the more likely it is going to be aligned with the stellar disk, because the magnetic field geometry sort of maintains its structure from the large scale. So it retains memory of this clockwise stellar disk. And the magnetic field ends up sort of dictating the direction of the flow at intermediate radii. And so in that case, it's more often aligned. I'd say maybe 60 to 80% of the time. And then for the weakly magnetized case, the field by the time it reaches equipartition, completely forgets about the initial geometry. It's like some random direction. So I would say there it is much less likely, maybe 30, 40%, something like that. But it's really hard to say without running a boatload of simulations. And also, technically, there is one correct time to restart from the initial conditions. It's when the stars are oriented exactly as they are today. But the problem, the reason I don't just stick to that is because of how chaotic it is.
Yeah.
So I feel like varying the parameters a little bit around that give me more of an idea of what could possibly happen. What time is it? 40. So, yeah, so just looking at the actual angles, similar thing. Okay, I'll stop with a few observations, literal not my observations, but comparing to observations, and my own observations as well. Okay, so, oh, you can't see that at all. Oh, that's unfortunate. So these are different heating models. This is 230 gigahertz flux for 4 of the different simulations. What you can't see is there's a little line that shows the observations right there. You have to take my word that...
It's hard to observe. What is the time in hours or days?
Oh, right. Yeah, why is that not in hours? That is actually in the next... No, what? It's a few hundred hours.
Okay. You mean the 400 is like 10 seconds?
Yeah, up here. I could have sworn I had this in hours. Oh, well, that's something to change. Okay. But yeah, so the flux is somewhere between, I think it's like 2 to 4.5 is where the observed value, like the 230 gigahertz value fluctuates. You can make it into a statistical distribution somewhere between 2 and 4.5 almost all the time. So none of them actually stay within that range all the time, which is a little discouraging, but they stay reasonably around that value. And to be fair, none of the torus models either match the time variability, so that is a recurring problem. But if the mad state, for instance, in this case, if the mad state was to persist for indefinitely, it would relatively stay pretty nicely within the bounds of the observed values. But my conclusion from this is that it's doing a reasonably good job of matching at least the value of the fluxes without any parameters that I can actually tune. I'll put it that way. There's parameters that change things, but I can't tune them in a way that makes me able to match the flux. Like I can't just say, oh, if I just change beta wind this way, I'll get better flux, like that. Same thing with unresolved. It actually does an even better job of the linear polarization fractions. And you can actually see the limits this time. So you can definitely get certain models which are always within the... So this is the integrated image linear polarization fractions, since we don't have the resolve to compare to. And also that would be more complicated to compare to. But I think this is the most interesting observational quantity to compare to because sort of a unique probe. It doesn't just probe the horizon scale, it probes a range of scales. Rotation measure, very quickly, is the amount that the angle of polarization will change from emission to observation. And if it's a point source, the theoretical result is this integral of number density times magnetic field perpendicular or parallel to the line of sight times some relativistic function. When electrons become relativistically hot, this gets suppressed. So observationally, you define it as some derivative of the electric vector polarization angle. That's what that stands for. With respect to lambda squared, which is the wavelength squared. So you can measure it even if it doesn't have this point-like behavior. 5 minutes? Okay, so this is the last slide. So all I want to say is that's okay. So there's 2 different scenarios that you can get. So the observed value for Sagittarius A star is this yellow or this white here. Sorry, that's not consistent in the 2. So it's relatively high. I think it's 5 times 10 to the 5 in units of meters. What is the units? Meters squared. No, rads per meter squared. There we go. And it has some variability, but I would say that the statistics on the variability are not there. We know that it varies on our timescales. But the important thing is that it varies on our timescales in terms of magnitude, but it does not vary in terms of sign for at least 20 years that we've observed it. So it's always the same sign. It's always negative. Now, the actual value of the sign isn't that important, whether it's positive or negative, that you just flip a sign in the initial conditions and you would get this, the exact opposite. So I wouldn't focus on the sign, but here you see that there are sign flips in the simulation. This is the simulation here. So yellow is one sign, blue is another sign. All these colors are really weird because they were white backgrounds and I inverted them. That's why they're all these like funkadelic colors. But yeah, white or yellow is negative, blue is positive, so lots of sign flips and relatively low magnitude compared to observations. And in this case, you have almost no sign flips, consistent sign, even higher than observations. So what's the difference? The difference is that here the rotation measure is dominated by horizon scales. Here it is dominated on thousands of RG scales, thousands of gravitational radii scales. And how does this, but you still get variability on the hour time scales because the horizon scale does contribute, it's just subdominant. So this is exactly the type of thing you need, is you need large scale magnetic flux that provides a consistent rotation measure plus a chaotic component from smaller scales that is at least a little bit comparable in magnitude. So the only difference in these simulations is that this one has a consistent, in terms of time, large scale magnetic flux that contributes to the rotation measure, while here you have a whole bunch of cancellation and no consistent sign in the large scale rotation measure.
So if you were to look at the amount of variability at a given time scale, doesn't that, the fractional variability, doesn't that tell you kind of the fraction of the rotation measure that's coming from a certain scale? Like if you associate time scales with radii?
Yes. Yes. Yeah, so I think that analysis could be done on observational data, probably. And then you could say, you need this percentage from this radii, this percentage from this radii in some distribution.
Yeah.
I don't think that analysis has been done. That would be interesting to look at. And yeah, so I think it has to be on the order of thousands of RG in order to have this consistent sign and not just a crazy coincidence.
But your emission comes mostly from near the
Yes, so the emission comes from very close to the black hole, but the rotation measure can be dominated by larger scales. And the reason for that is because of this factor 1 over theta e squared. Because as soon as the electrons become relativistic, the rotation measure basically shuts off. And so what I didn't show it before in that plot, but I skipped over, was the electrons become relativistic at hundreds of RG or so. And so that's what really helps this work. But this is something that I need to analyze in greater detail because I think it's one of the most interesting probes of the accretion flow because it is not just the horizon scale, it's a combination. And I think that's pretty interesting and cool.
That's amazing.
Okay, conclusions. I won't read them, but I'll just stop there. I've already gone over, so.
Angela?
So on your just last slide, for the constancy of sign, does the inclination matter? I'm wondering, for example, if there's a jet coming towards us that could evacuate that region, and then we're back to the top left.
Yes. So I thought so. I thought this was a great story that I thought it would match perfectly. And then I realized I was like, okay, so the case where the jet is aligned with us, that will have the low rotation measure that varies like this. The one that is perpendicular will have this one. But then I realized that it worked in the opposite way. Like the one with the jet pointed at us actually had a higher rotation measure than the other one. And part of that is because this integral doesn't really work on those scales. As you know, on those scales, if it's not a point-like source, in other words, you have the source and the rotation measure happening, or the rotation happening in the same region, you can't just treat it as this point-like integral. Plus, you have the GR effects and all this. So it doesn't seem to match that paradigm very nicely at all, unfortunately. What I will say is that it does, the rotation measure in all the simulations does follow the lambda squared. So I know this is a concern for M87. Does it follow lambda squared? Can we even treat it like this? But for Sagittarius A star, it seems like the observations and these simulations seem to work with the lambda squared. So I will say that. Just wanted to say that particularly for you.
Avi?
So in your last sentence, you said another thing that is robust, and you didn't include it in your list.
Okay,
which
what did
is
I
that
say?
the electrons are relativistic.
Oh, right.
And
yes.
I mean, that is interesting. Why? Because when you have relativistic electrons, they can collide with each other and make pairs. Do you include pairs?
I do not.
Why?
Because that was one, it's more complicated. That's the obvious reason.
but reality.
But yes,
Yeah.
so most likely that will be happening in the jet, and there are people actively working on that, and to see what effect that will have. I think it is particularly going to be interesting for M87 more than Sagittarius A star, just because you have, we at least know that the jet there is very powerful and active.
I mean,
But
if you make pairs, it will increase the number of electrons and positrons
Yes.
beyond what you started with based on the gas density. So it will change your emissivity, basically. And that could be important. I don't know, an important part of the story if you increase it by orders of magnitude. So it's just worth checking.
Yeah, I will say that people are actively working on that.
Yeah, the people that are working on that are listen to me when we started doing that a few years ago, but it would be nice for you to include it as well,
Yes.
because we did it here.
Oh, this is the plot that
Yeah.
this is the electron temperature function of radii, and this becomes relativistic around here. And this is the 3 different heating models, so it's roughly the same.
Yeah, so you can easily calculate the pair production rate and then the effect on the emissivity.
Daniel?
Yeah, so in these models that end up in the mad state that have been humming along for a while and they align their disks with the spin, is there any way that you would be able to look at images you generate from these, or maybe a sequence of images, and actually tell them apart from one of the more traditional
Maybe.
aligned tori models?
Yes. So I haven't looked in great detail in all of the actual resolved imaging. That is the follow-up work. I purposely decided to leave those out of this because I wanted to just focus on like the dynamics and just more simple things, because the paper as it stands is already like 25 pages. I'm like, I can't be anymore. And if I found something exciting, I would be like, I can't leave it out. So,
Right.
but I feel like it must, at least at some level, because the orientation changes so much. I would like to think it must, but it might.
But at late times it didn't, right?
Oh, right. Yes.
Yeah, so I'm just
So,
saying, at
like,
late
difference-
times do they tell? Is there a way to tell the difference? I guess the thing I'm actually getting at here is my follow-up question, which is, do you bake in an evolutionary timescale from I don't know, the orbital timescales, whatever star happened to have its gas contributing, or whatever wind timescale that's relevant, that sets a timescale in the inner accretion flow, or is that information all completely lost by the time it circularizes?
It's very low.
I would say if they're, so this is hard to study because you have these multiple timescales and multiple simulations. So by the time you get down to the GRMHD simulation, essentially everything at larger radii is fixed. And one, you can't even run it long enough for that to really start affecting your conclusions. Like I would like to be able to run the GRMHD simulation for, I don't know, 50 years and then see what happens. But, so I do think that is likely an important time scale is the time scale, probably like half an orbital time scale or something.
But
where
that's very long, isn't it?
It's very long,
It's
yes.
decades.
Yes.
Yeah, so.
But that could change, like if it's mad or not mad. I mean, we don't really care if it's not going to be mad in 100 years, but that might set the time scale. But there's also the time scale for what star becomes important and what doesn't. That's slightly shorter, maybe 10 to 50 years. But these are very long time scales. So not entirely sure. That's what I'll conclude with.
So you started this by thinking about zooming out, so,
Yes.
and then you zoomed in.
Yeah.
So in the magnetically arrested case where there is this like escaping
Mm.
outflow,
Yes.
like
Yes.
can you think about doing kind of the remapping exercises you did and ask whether that affects the large scale?
I've definitely
scale
thought about
structure?
it.
Yeah.
Yes,
yeah.
I would like to do that. I wonder if it would actually work well, if it would just if it would produce like a consistent result. So there was this paper, this series of papers in, I don't remember what year this was. I think it was Feng Wang who did this idea, but in both directions.
Uh-huh.
You have a large-scale simulation, small-scale simulation. You run one, feed it into the smaller-scale simulation, run that, feed it into the large-scale simulation, feed that again back into the smaller scale simulation, and just keep doing that until it stops changing, roughly. And I think that is a very interesting idea. I have no idea how well that would work, because I feel like it works very well when you have only one direction going in, when you're like, okay, this is not going to feed back to large scales. But as soon as you're like, there's all this feedback, I would hope it worked, but I'll try. I'll definitely willing to try.
Before you asked if there was convergence, it would be interesting
True.
just to ask,
True.
is there, like, if that jet were persistent on a really long time scale, like decades, would it affect the flow on that scale or not?
Yes.
Like,
that
I
is
don't know
very
if it
true.
has enough
True.
ramp
Yeah,
pressure.
I mean, if it doesn't affect anything, then that's a conclusion in all itself.
But also you can connect it to the Fermi bubbles.
Yeah.
Yes.
The Fermi bubbles
yes.
could have
Yeah.
originated from.
And there's also all these like little mini cavities all over the place.
But I
Not
mean,
all over the place, but there's
it's not-
these mini cavities.
It's not obvious because of what you told us about the fact that there's so much mass that isn't making it
Yes,
down.
yeah.
So you might get to the point where it peters out.
Yep.
I think kind of interesting.
Yeah, that's kind of my bet for why we don't see the jet.
Yeah.
But also, I mean, it's also pointed at, so maybe we won't see it.
Have you considered putting the stars on tighter orbits and doing everything self-consistently? So if you move in the star from, let's say, 10 to the 6 to maybe 10 to the 3 RG.
Yeah, that would be, I've
there's-
done that with stars with a lot less mass loss rate. And if you just put in like a star at a much smaller orbit with a less mass loss rate, with all the other stars still there, it doesn't really affect things. But then putting another star closer in with a significant mass loss rate, I have not. I think that would, so one of the key features of these Wolf-Rayet stars is that their orbital speeds are roughly equal to their wind speeds. So as you go closer in, the orbital speed will start to dominate over the wind speed, and you will definitely get more circularization.
But below a certain radius, it will be tidally disrupted. So
Yes.
you can't go closer
Too
than
far.
100, maybe.
Yeah,
I don't know what the tidal radius is for these.
yeah.
Wolf-Rayet.
But it could definitely go in further than like a parsec or whatever they're at.
Oh yeah.
Yeah. So yeah, I am interested in just in the general problem and also the specific problem of just like what happens if the stars are further in, what happens if the stars are further out, because you're in this very unique parameter regime where they're roughly equal. Because I think at larger, if they go out, you go out further, you're more in like the Bondi-Hoyle-Littleton case where it's just being bombarded, and then further in, it's just going to basically instantly produce a disk.
Yeah.
Because I think there are two time scales. One is the time scale of the black hole, and one of them will be the free fall
Yes.
time from, let's say, the orbits of the stars. And still, even if you decrease the free fall time by orders of magnitude, the two time scales will still be very far separated.
Yes.
So you might get more like statistics on
Oh, I
the
see.
time
I see.
scales.
Yes, that is a good
That you
idea.
could
I
do
see.
it, you know,
You mean
that
to
you
do
could-
it just to get the statistics and then infer? Oh, I see.
Yeah, you know, to
Oh,
cheat
yes.
a little bit, just
Ah,
you know that
yes.
you can say more about the randomness of the scheme.
True.
You know that you can do.
That is a very good idea.
orbits.
Yes.
I actually had a question on the tilt. So did you try anything other than 45 and 90?
So-
I'm wondering if there's like a characteristic angle.
Yeah, so that's the thing, is that I can't definitively say that if this were 90 degrees, it would align because I don't have a 90-degree mad case. Unfortunately, like I could just keep running until I get one. But that's, unfortunately, I don't have a way of like a priori knowing what the tilt is going to be. So I don't have a way of being like, okay, if I just run this simulation, then I'll get a mad tilted at 90. Which is both the problem and like, that's a problem in some sense, but it's also what I started out trying to do. So it's not really, it's like kind of built into the problem. But I would like to find a simulation that does do that. But it does seem, what I will say is that when the flux is peaked, it does seem to be more or less aligned in this case too, which I feel like is a strong statement given how misaligned it was.
Okay, if we don't have any questions, let's thank our speaker again.
was excellent. Thank you.
Thank you.
Very